So, continuing on, I'd like to talk a little bit about explosions, but first I want to categorize collisions. Collisions come in two main types. The first type is where the objects bounce off of each other after the collision. Curling rocks don't stick together. Billiard balls, when you're playing pool, they don't stick together. A baseball and a bat, the baseball doesn't stick to the bat unless something's gone horribly wrong. Some car crashes. There are some car crashes where the wreckage sticks together. There are some car crashes where the wreckage bounces apart. There's a fancy physics word for that. For objects that bounce off each other, we call this, where's my cursor? Oh, didn't want to hit that button, Mr. Dewick. Hit the wrong button. We call this elastic collisions. Can't type today. A collision where the objects bounce apart off of each other is called an elastic collision. Then the second type of collision is where the objects stick together after the collision. A football player tackling and holding on to a ball carrier. A dart hitting a dartboard, assuming the dart doesn't bounce to the floor. Some car crashes. A bullet entering and sticking inside a target, not going all the way through the target, but entering and sticking inside the target. Those are examples of collisions where the objects stick together, and we call these inelastic collisions. There's a bit of a problem here, Ange, in that when I say to you that I'm dealing with an elastic collision, it's tough to tell whether I said an elastic collision or whether I said an elastic collision, which is the second one. They kind of sound alike. So sorry, that's the English language. We're stuck with that. Usually I'll try and make it very obvious what I'm saying. How can you remember which is which? I always remember elastic. I think elastic band, rubber bounces, and they bounce apart. Inelastic, they stuck together. Okay. I will use those words on tests. I won't ask you to specifically define these terms, but I may tell you, oh, an elastic collision occurred, and so when you ask yourself after the collision stuck together or separate, you can say, oh, he said the word elastic, must be separate. Okay, that part you'll have to deal with. Put your pencils down, look up. Today we're looking at explosions. So here is a rifle. A rifle bullet leaves the muzzle with a velocity of 6 times 10 to the 2 meters per second. If the rifle is held very loosely, with what velocity will it recoil? Is this a collision? No. Is this an explosion? Yeah. Is this a jeune? Yeah. This is a job for conservation of momentum. The total momentum we start with has to equal the total momentum we end with. I'm going to call, let's see, this mass B for bullet, and I'm going to call this mass R for rifle. Is that okay? Before we pull the trigger, what's moving? The rifle, the bullet, both, or neither? Oh, so are you saying my initial momentum is 0? Yeah. You know what my final momentum is going to be then? 0, but I'm going to break it up into 2 different moving objects. I think one's going to be positive and one's going to be negative. Okay? Is that all right so far? Bang! We pull the trigger. After we pull the trigger, what's moving? The rifle, the bullet, both, or neither? I think both stuck together or separate. I think separate. Yes? So we're going to have the momentum of the bullet final and the momentum of the rifle final. One of those will be positive, one of those will be negative, and that way they can still add to 0. I don't have a gain or a loss of momentum. Okay. Momentum is what times what? So this is going to end up being mass bullet v bullet plus mass rifle v rifle. What does this question want me to find? Okay. If I'm going to get this by itself, I guess, Patrick, I'll minus this to that side. It's just going to become negative over there because there's a 0 there. And then divide by the mass of R. I think I'm going to end up with this. Negative mass of the bullet, V bullet, over mass of the rifle. That's going to be how fast the rifle moves off. And all the negative is telling me is it's in the opposite direction of the bullet. If the bullet went east, the rifle goes west. If the bullet went north, the rifle goes south. Or if I go generically, if the bullet goes forward, the rifle goes backward. All right, let's find out. Does the rifle have a bigger or smaller mass than the bullet? So is it going to be moving faster or slower than the bullet? I think way slower. I better get an answer that's smaller, otherwise I've messed up. Negative. Mass of the bullet, 0.06. Velocity of the bullet, is it 600? 6.0 times 10 to the 2, which I think is 600 in less writing. 6.02? I think just 6.0. Yes? Yeah. Okay. Redeem yourself, Patrick. What was the mass of the rifle?
3.
What do you get? I might be able to do this in my head. 600 divided by 3 is 200. Negative 12 or negative 1.2? Negative 12? Basically, if it's an explosion situation, your initial momentum was 0, your final momentum was 0. There you go. Question, Kieran? Is that okay? And again, the negative is just the rifle's going to go that way if the bullet goes forward. I showed you ages ago a video for Newton's third law of people firing a high-powered rifle with big recoil. Spencer is sitting in a canoe, floating on the water next to a dock. He decides to stand up and step out of the canoe and onto the dock. So I will mime this. Here is Spencer in his canoe. The dock is right there. He decides to step sideways onto the dock. Why is he going to get wet? It's not going to tip the canoe. I used to teach canoeing at a summer camp, and I saw this happen all the time, and I would just laugh hysterically. Okay. You hear, Haley? Ready? Right now, what's the momentum of Spencer and the canoe if they are at rest? 0. So what will the final momentum be still?
0.
So if Spencer gives himself a momentum to his left, which way will the canoe move?
Right.
What has a bigger mass, Spencer or the canoe? So what's going to move? This canoe has a bigger mass? Human beings weigh more than a canoe, trust me. What has a bigger mass, Spencer or the canoe?
Spencer.
Trust me. So what's going to move away faster, Spencer moving to the dock or the canoe moving out from underneath him? The canoe's going to move faster. You've experienced this if you've been horsing around in a lake or in a pool and you've tried to balance on a floating toy and then you've tried to dive off because your initial momentum is 0 right at that moment. What must your final momentum still be? 0, but because you have a much bigger mass than the floating toy, when you try and give yourself a forward velocity, the floating toy is going to get a way bigger, way faster backwards velocity. It's going to flip out from under your feet and you belly flop. Some of you are smiling right now. Oh, is that what was? That's why. Yeah, that's why you couldn't. You okay with that? So, canoe will move away from dock since momentum must still equal 0. Oh, and since the canoe is lighter, it's going to move faster than Spencer moves onto the dock. I saw this happen all the time. Okay. By the way you get out of a canoe is rather than step out, you turn Momentum is still 0. You sit on the edge of the dock, and now you've got some friction between your body and the dock, and you can lift your feet out. Here's another example of an explosion, except this is a very slow explosion. A boy and a girl are standing in the middle of the frozen pond right here. They're facing each other, and they both give each other a shove, so they move apart. The girl moves off with a speed of 2.4 meters per second. With what velocity does the boy move off with? Let's ignore friction. Okay. Is this a collision? No, but it's an explosion, a slow explosion. There's still a job for conservation of momentum. You know what? We're going to take a gamble. We're going to skip writing the sum of all the initial momentum, the sum of all the final momentum. We're going to see if we can break it down right now. Before the explosion, what was my initial momentum? 0. Afterwards, what's moving? The girl, I'll use a G for girl, a B for boy. The girl, the boy, both or neither? Both, stuck together or separate? Okay, momentum is what times what? So can I go mass, girl, velocity, girl, plus mass, boy, velocity, boy. I skipped a couple of steps there. You okay with that, Connor? On a test, I go really systematically. In my homework, I try and see if I can get good at this. Connor, what does this question want me to find? In fact, I think this is almost identical to the one we just did with the rifle. I think we're going to minus that to that side and divide by the mass. Yeah. I think we're going to get negative m girl v girl divided by mass of the boy. That's going to be the velocity of the boy. So the velocity of the boy is going to be negative 60. What's the velocity of the girl? Sorry?
2.4.
Which way is the girl moving? If you called that negative 2.4, I would also be okay with that. Just if you wanted to say, just so I don't make a mistake, I'll let to the right be positive and to the left be negative, and that'll give us a positive velocity for the boy. But you've decided to let left be positive. That's fine with that too. What was the mass of the boy? 45? Yep. Give me 1 second here. Pause the video. Hang on 1 second here. What do you get? Negative 3.2 meters per second, so it's going to be 3.2 meters per second. Direction? Right? Based on the picture? Okay. What does B want me to find? What does B want me to find? Impulse. Hey, that's change in momentum. I don't see a force and a time anywhere. I'm not going to use that. I think I'm going to use mv final minus mv initial. Jenna, why can I cross that out? Yay! Great. So the change in momentum, the impulse of the boy, is the boy's mass, 45, times the boy's velocity, 3.2, which is what? Sorry? I can't hear you. I just need the number first of all. What was the answer?
144.
Thank you. 144, and momentum is kilogram meters per second. Direction. Boys, change in momentum was to the right. What's the impulse of the girl? You don't need to do any calculations. You all know the answer already. We could either say negative 144, or if we wanted to add a direction, we would say, yep. So impulse of the girl is 144 kilogram meters per second left. That's really what the law of conservation of momentum says. It says impulse is equal and opposite, and that's what means you don't lose any momentum. D, if the push lasted for 0.25 seconds for a quarter of a second, with what average force did the boy push the girl? What did we just find? Impulse? And impulse has force and time as well. Now I think I'm going to pull out the fact that impulse is force times time. How would I get the F by itself? Okay. So the force is going to be the impulse divided by the time. What was the impulse? 144 divided by 0.25. $572? Sorry? 586? Is that what you said? Okay. When I'm saying pardon me and you say it the same volume, it doesn't help. So 576, is that what you? 576. Thank you. Sorry to sound snotty there. Newtons. Direction. Well, I think the boy pushed the girl to the left. The girl pushed the boy to the right. Is that right from the picture, I think? Yeah. So if they asked for a direction, I could get that as well. I'm just going to give you the magnitude here. Hey, let's go into space. A space capsule consists of a 2,500 kilogram main capsule and a 1,500 kilogram space probe. The vehicle is traveling 120 meters per second when an explosion occurs. After the explosion, the probe moves forward at 280 meters per second. What's the new speed of the main capsule after the explosion? After the what? This is a job for conservation of momentum. In my mind, I'll just imagine the sum of all the momentum before equals the sum of all the momentum after. I'm going to use, how about the letter C for capsule and the letter P for probe? Before the explosion, what's moving? The capsule, the probe, both, or neither? Stuck together or separate? So I'm going to have the momentum of both initially. Bang! There's an explosion. After the explosion, what's moving? The capsule, the probe, both, or neither? Stuck together or separate? Very separate. So I'm going to have momentum of the capsule final and momentum of the probe final. By the way, what happened to the speed of the probe? Look at the before, look at the after. Did the speed of the probe increase or decrease? Increase. I'm going to ask you the same question. I'm just going to phrase it differently. What happened to the momentum of the probe? Did the momentum of the probe increase or decrease? So what must have happened to the momentum of the capsule? So what must have happened to the speed of the capsule? I already know the answer to the capsule is going to be less than 120. Right? Got a bit of a built-in error check by understanding the physics there. Momentum is what times what? It's mass times velocity. So this is going to be mass of the capsule plus mass of the probe, both V initial. And that's going to be mass of the capsule, velocity of the capsule final, plus mass of the probe, velocity of the probe final. What does this question want me to find? So I want to get that by itself. I think I'm going to minus that over and then divide by the mass of the capsule. Okay, let's see if we can do this in one fell swoop. So VCF, the final velocity of the capsule, it's going to be both drop down like a domino, minus mass of the probe divided by mass of the capsule. What was the mass of both of them put together? Is that 4,000? I've scrolled down. What was the initial velocity of both of them? 120. minus probe is 1,500, and its new speed was 280, divided by 2,500. What do you get? I know it's going to be less than 120, right? 4,000 times 120 minus 150 times 280 divided by 2,500. You get one. No, that's wrong. Did I type something in wrong here? I wrote 150 instead of 1,500. I missed a zero there. And so I missed a zero on my calculator, which is silly. Thank you. Oh, 24? What if I had gotten meters per second? What if I'd gotten a negative answer? It would have meant the explosion was big enough that the capsule ended up going forward very fast, and the probe ended up going forward very fast. The capsule got knocked backwards. Or I could have ended up with zero. That would have just meant all the momentum got shifted to the probe. What does B want me to find? On what? Okay, so that's going to be the change in momentum, which is going to be M probe V final minus M probe V initial. I've scrolled down. What was the mass of the probe? 1,500. What was the final velocity of the probe? Minus mass of the probe, 1,500. What was the initial velocity of the probe? And before you answer, double check, is there any change in direction? Do I need to let any of these be negative? Nope, Christina's shaking her head. What was the initial velocity? 120? Okay. What was the magnitude of the impulse given to the probe? You get 402,000? No? Oh, I'm off again. I missed a zero again. Good gosh, Duick. I'm in a slump here. You get 240,000? Yes? Kilogram meters per second. Direction. Oh, you know what? It just said magnitude, so it doesn't care about direction. Forwards, I guess, or it gained. Why can't I do part C without doing any work whatsoever? What's the answer to part C? If you said negative, Eric, I'd take that. Since it said magnitude only, I wasn't too fussy. But yeah, it lost that much. That's why the probe gained that much. With you so far? Mountain climbers use nylon safety ropes due to their tendency to stretch under stress. Why wouldn't you want a rope that didn't stretch at all? You can make the rope strong enough that it wouldn't snap. So why wouldn't you want a rope that was so strong that it didn't stretch or snap? If I fall, I want the rope to change my momentum, which is also force times time. I want it to bring me to a stop, change my momentum. As T gets bigger, F gets smaller. So if it stretches, if it lengthens, Luke, you're right, if it lengthens the time of collision, it'll be less of a jerk to my body. Okay. Why does conservation of momentum explain why it's so difficult for firefighters to hold hoses that are ejecting large amounts of water at a high speed? You can sort of think of a fire hose as a controlled explosion. Before you turn the water on, what's the momentum of everything? So what's the momentum after? Still zero. If the water gets a momentum forward, what does the hose get? A momentum in which way? Yeah, backward. And there's a lot of mass times velocity coming out that fire hose. It's also Newton's third. It's both, because conservation momentum came out of Newton's third. We said forces come in pairs. Oh, and if it's the same object in a collision, the time is also the same. So force times time, impulse will be the same, which means momentum is conserved. So yeah, you can say Newton's third, forces come in pairs, so momentum is conserved. If the water gets an impulse forwards, the hose gets an impulse backwards. And if you're holding on to that hose, you're the one applying the force times time. Anybody here use a fire hose before? No? Okay. I think this is the last one. Yeah, last one. The diagram below shows two pop cans of unequal mass. One is mass M, the other is mass 2M. An explosive charge is detonated them and the cans fly apart. Boom! What can you tell me about the velocities after the explosion? Are they the same or different? Patrick says different. Why? Which one's going to be going faster? Lighter can or heavier can? Lighter can? In fact, what's the relationship between the two masses? One's twice as heavy, so the lighter can is going to be going how many times faster? You okay with that? Patrick is saying lighter can will have twice the velocity. You okay with that? Using principles of physics, well, the initial momentum is zero, so they both get the same impulse. Heavier mass means less velocity. Lighter mass means more velocity, and I can even be more specific. Twice the mass means half the velocity. Half the mass means twice the velocity. If you're twice as heavy, you're going to move half as fast. Homework to try. Give you lots of time so you don't have any homework, or at least not much homework for a long weekend. Number 1 is good. In number 2, I'm giving you some pictures. So we have collisions. I'm using arrows. If they're attached, touching, I'm saying they stuck together after the collision. So I want to just give you some practice with inelastic and elastic collisions. So number 2. Four is good. 5 is good. Try 8. Just looking here what I got. We'll do 9. Uranium fission. You know what? We'll pause here. Give you some questions to try, but not much homework for the weekend, okay?